What happens to ANOVA in the age of machine learning? Aloha! In this video, we will explore how traditional statistical methods like ANOVA relate to modern data science and machine learning approaches. In recent years, many data scientists have shifted from traditional statistical techniques toward machine learning methods, especially for predictive tasks. Procedures like ordinary least squares, OLS regression, which once dominated social science and business analytics, can now be effectively replaced by tree-based models such as decision trees, random forests, and XGBoost. These modern algorithms excel at capturing nonlinear relationships, handling large datasets, and automating variable selection. However, when it comes to inference, procedures like the t-test, ANOVA, ANCOVA, and MANOVA, data science and machine learning, DSML, do not yet offer direct equivalents. These classical statistical tools answer questions about whether group differences are statistically significant. The absence of such tools in DSML is perhaps one of the reasons many researchers remain committed to classical statistics, especially when their goals center on explanation rather than prediction. To understand where the line between prediction and inference begins to blur, it's helpful to look at the general linear model, GLM, the broader framework under which both ANOVA and OLS regression fall. GLM is a unified statistical framework that models the relationship between a continuous outcome and one or more predictors, which may be continuous or categorical. OLS regression is used when all predictors are continuous or when categorical variables have been dummy-coded. ANOVA, on the other hand, is simply a special case of GLM where the predictors are entirely categorical. So, rather than being fundamentally different procedures, ANOVA and regression are two branches of the same statistical tree. Both are concerned with estimating the relationship between inputs and an outcome, but differ in the structure of those inputs. Within the GLM framework, ANOVA-type problems can be reformulated as regression problems. So, if data science and machine learning methods can handle regression tasks, they can also be applied to problems traditionally addressed by ANOVA. Tree-based models in DSML, such as XGBoost, can also include grouping variables like treatment group, education level, or region as predictors. These variables can be incorporated by encoding them either numerically, if ordinal, or as one-hot or dummy variables, if nominal. The model will learn how to split the data based on these group variables if they provide useful information for improving predictive accuracy. This means that while DSML methods do not perform inference in the classical sense, they still utilize group differences when those differences are helpful for prediction. The philosophical and practical distinction between these approaches is worth highlighting. In classical GLM-based models like ANOVA, the question being asked is, are the group means significantly different? This is a question of inference. It seeks to generalize findings beyond the sample and assess whether observed differences are likely to have occurred by chance. In contrast, DSML models ask, does knowing the group help us predict better? A question of prediction. DSML does not provide p-values or f-tests. It doesn't quantify the likelihood of observing group differences under the null hypothesis. But this isn't necessarily a flaw. In fact, many statisticians have criticized the over-reliance on p-values, noting that they are often misunderstood or misused. In response, DSML offers alternative tools for interpretability, such as Shapley additive explanations values, which quantify the contribution of each feature, such as group membership, to a model's prediction. SHAP values don't tell you whether a result is statistically significant, but they do tell you how important a variable is to the model's decision-making process. When including categorical grouping variables in machine learning models, encoding becomes a key consideration. One-hot encoding, which creates a binary column for each category, is a safe and interpretable method when the number of groups is small, say fewer than 10 or 20. However, in scenarios where the group variable has many levels, such as zip codes or regional identifiers with hundreds or thousands of values, one-hot encoding can lead to unwieldy models and overfitting. In these cases, target encoding, also known as mean encoding, is often more practical. Target encoding replaces each category with the average outcome associated with that group, effectively turning a high cardinality categorical variable into a continuous feature. While target encoding is powerful, it must be used carefully to avoid data leakage, often by applying it within cross-validation folds. To illustrate how this plays out in practice, imagine you're analyzing sales performance across different retail regions. Using classical ANOVA, you might test whether average sales differ significantly across regions. You would get a p-value and, if it's below your threshold, conclude that regional differences exist. In a machine learning workflow, you could instead include the region variable in an XGBoost model that predicts daily sales. If region helps the model make better predictions, XGBoost will use it in its splits. You could then use SHAP values to interpret the effect of each region on predicted sales. If you have hundreds of regions, you might use target encoding to represent each region by its historical average sales during training. This shifts the focus from hypothesis testing to prediction quality, but still allows you to see how region matters in the broader context of your model. In conclusion, while data science and machine learning may not replace classical inference methods like t-tests or ANOVA, they offer powerful alternatives for prediction and pattern recognition. These models can still incorporate grouping variables as features and assess their practical importance in predicting outcomes, even without the use of p-values or traditional statistical tests. For those willing to step outside the bounds of classical methods, tools like SHAP and smart encoding strategies open new doors for interpreting complex data. If you found this video helpful or thought-provoking, feel free to share your thoughts, ask questions, or continue the conversation in the comments. If you found this information helpful, please like, share, and subscribe. Let's keep learning together. Mahalo.